Alright, so we're gonna look at BST again, okay, today. So this is going to talk about, on the previous video we looked at is what's BST, and we use recursive, right, to insert, to find the size first, and we also look at recursive to find if the BST contains the elements that we're looking for. And then we also use recursive to add a new node into BST. Also, we look at the remove operation, which is the most complicated one. So let's review the remove again. So when we remove, there are three scenarios, right? If the node that we try to remove is a leaf, so removing a leaf is simply a matter of setting the appropriate link of the parents to null. Which, for example, if we try to remove Z from this tree, then we just set R pointing to null. So the code that we're going to look at is first algorithms here. Look at removeNode. So how do we know that the node that we try to remove is a leaf? That means when we get left and get right, both are null. So that is the remove node. Then we just return null back. Else, look at the second scenarios. Removing a node with only one child. Make the reference from the parent skip over the remove node and point instead to the child of the node we intend to remove. So that scenario is shown here. So we try to remove an R which has one child. So we have to make the link that point to the remove node to point to the child of the remove node. So now Q is pointing to Z. Right? Either it's going to be on the right or left, it's going to be the same scenarios here. We're always going to point to the one to the right, because the one to the right, like in the case of if L has two branches, right? That's going to be another scenarios, right? With removing the node with two children, which we are going to look at next. So now let's look at removing a node with one child. So if it's always one child, then we always point to the child of the remove node, which it doesn't matter because it's only one child. So always set the link of the parent of the remove node to the child of the remove node. So let's look at the code first. How do we check? So if tree.getLeft is null, so that means this is the only node, right? I mean the child, the remove node has one child on the right. Then we just return tree.getRight. It's going to return back to set. So else if tree.getRight is equals to null, that means we remove a node with child on the left, but only one child. So we return tree.getLeft. Let's return back to the parent, and the parent will set. Okay. So let me look at the complete code here a little bit, then we'll see how this being coded. We are interested to look at remove. So this is the remove node. And we have recursive remove. And we have remove. Alright, so first remove is going to be called. We pass the elements that we try to remove. So start to call recursive remove. So let's look at recursive remove. Which is here. So we're passing a tree. So first time we're passing in, which is the root. The root go in, first have to check if the tree is empty. If it's empty, then return false. So that means we cannot remove. Nothing to remove. False, return back. Return the tree back. And return found to false. Because found is being declared as the attributes of this class. Okay. So when set found to false, then this also false. And restaurant is going to know. Technically this one is never been used. Now we look at the scenarios of if the tree is not empty. Right? When we remove, we look at if the tree is empty, then we cannot remove, found into false. Now if tree is not empty, then we have to get into the first scenarios. If this is a leaf, or node with one child, or node with two children. Okay. So let's look at the scenarios of node with two children again. So when we remove the node with two children, replace the node's info with the info from another node in the tree so that the search property is retained, then remove the other node. So that's the algorithms. Like we found that we want to remove Q, we replace value of Q with the max value from left branch of Q. Then it's retained the properties, because the max value from left branch of Q has the value less than or equals, and the max should go to the root instead, which is going to be less than the right branch and greater than all the left branch. After we replace, we have to remove the node P. So that means we technically just call recursive remove P and pass P to remove, because P becomes a leaf after the first arrows that removed it and leaf. So pretty much just the two things, replace the values and remove the leaf. Wait, no, we don't show it. Alright, so now come back to look at algorithms for that. Else that means this is the node with two children. find predecessor. Predecessor pretty much just find the max of the left branch. Then we set the info to replace that values. That's the set data that we talked about. And we start to remove the node, which is the node that we said that's the predecessors. Remove that, pass the predecessor. And recursive remove will remove the tree. And when it's remove the tree, it's return null. I mean remove the leaf and it's return null for tree that's left. We can remove one of the tests if we notice that the action taken when the left child reference is known also takes care of the case in which both child references are known. When the left child reference is known, the right child reference is returned. If the right child reference is also known, then null is returned, which is what we want if they are both known. So when we implement remove, come back here, we also look at left child, right? We start to compare the elements to tree.getInfo. Then we try to search for the location where we want to remove. Now, if it's less than 0, so that means we have to go to the elements is less than info, go to the left. So tree.setLeft and get the left pass as the node that we want to recursively search to remove, and the elements to remove. We're just going to go back and do the same until it's found the location. If it's right, then we just do greater than 0 here. That means we have to search into right. So set right, recursive remove, and get the right. Okay, so once found, it's pretty much just return elements. Like, for example, if we reach the location that we found in the center of this image, right? So we said, I found that I want to remove R, right? Then it's not less than, it's not greater than. It's going to fall into the else. We want to remove the node. Right, we found location to remove. So pass the tree that we want to remove, which is the node. The parent node is being passed at that point because return, right? When we pass that, we pass the parent node. So let's look at how we remove the node. So remove a node has to check if tree.getLeft equals to null. So we pretty much checking for the scenarios of if this is what? If this node has a children or child on the left. If it's equals to null, then this node doesn't have a child to the left. In that case, that means this node has a child to the right, because we're checking for node with one child, right? So that's why we return get right back. So return z back to where? To the tree.set right. In this scenario, Q set